Let's start with some announcements. We have an exam on Friday. Study guide is posted. We will have a review session on Thursday for it, so please come prepared with any questions. I've gone over the study guide. Just like last time, you get a sheet of notes. Anything can be on that. I'm not going to collect it. There's an assignment that is also due a week from today. And if you wait until after the exam to get started, you're going to be in for a world of hurt. So please get started on that if you have not already, as soon as possible, because there are 4 parts to the assignments and there's a reasonable amount there. So get started, get stuck, come to my office with questions, and I will do what I can to get you unstuck. Does anyone have questions about what's going on in the course before we get started with stuff? All right, it's been a while. On Thursday, we covered some sets and hash tables material. We introduced the concept of sets, mostly to talk about why it doesn't really make sense to implement a set with a list and why we want something that could be faster than that. And we use that to introduce hash tables. Can anyone recall anything about hash tables from Thursday? What do we remember? What are they? Yeah, so we assigned every object that we could store there some kind of hash code. And that hash code is just an integer. And then we have some array that we are trying to store these in, and then rather than storing them in sequential order where we have the latest element that's been added at the end of the list, we are instead going to assign a location based on the hash code mod, the table size. So if we have space for 1001 elements, which would give us indices 0 to 1000, then you would mod that number of whatever we wanted to store by 1001 and put it there. What issues could we come up with when we tried to do this? What was the big concern that we needed to deal with?
Mapping on the same index.
Yeah, we had 2 different objects that map to the same index because there are a lot more integers than there are going to be places to store in our table, regardless of the size of the table, unless we have an infinitely sized table. We did have an infinitely sized table, great, all of our problems are solved, but that's not feasible. So let's go back through everything, because I feel like a lot of people were focused on the A function today, so we modeled using sets. So we wanted to be able to do all of these things. We wanted to be able to add, clear, contains, equals, take the difference, take the intersect, take the union, be able to remove, just the functionality we would expect from a map set. And then we wanted to potentially use an array with that, and we found that everything was going to be linear. Because worst case, we'd have to search through the entire array for everything, and every time we added or removed something, we'd have to move everything else over. And that seemed like there should be a better way to do things. We'll find this a lot in computer science as we move forward throughout the curriculum, as you take algorithms and advanced courses and electives. You'll find that you'll get a more intuitive sense of when could something be faster. Sometimes an algorithm that's cubic is going to be just as fast as we can reasonably do it. But sometimes you're in linear land like we are right now, and it feels slow, it feels inefficient. It's efficient compared to an algorithm where you have a worst case complexity of n cubed. But you build that intuition of, if we're just searching through the entire list every time for every operation that we have to do, it feels like we can do better than that, which is how hash tables have come to be. So we talked about how built-in Java objects have a hash code method that already exists. You just call the .hash code and you get back the integer that you can use to mod by the table size and figure out where you want to store it. Great. If you make your own objects, on the other hand, you're going to need to define what that hash code process is. So we were in the process of talking about exactly how to do that, given what the object is made up of. We introduced the concept of a hash table. So we looked at the extremes, an array of size 1, every element maps to the same index, everything collides. If you have an infinitely large storage, then there is no overlap. And we're fine. So in general, we're seeing this throughout this course, and you'll continue to see it in just about every course you take. There is a space-time trade-off. If you want to take more time, then you can end up taking less space. It will take more time to query something that you have less space for. You need to be more efficient with your storage, and that takes time to parse. If you can be less efficient with your space, then you can save time. As we can see with this infinitely large array, and everything maps to it, we don't have to worry about any time related to collision logic. We just look for it, hey, there it is. So in practice, we have both space and time limitations. So there's no right answer. We just have to, in general, come up with good practices for how to analyze the space and how to analyze the time. And based on our own constraints, come up with a way to solve the problem in a way that adheres to those constraints. We talked about good and bad processes for computing the hash function. We used the phone number idea. So we have space for a table of 1,000 phone numbers, and the bad example was to use the first 3 numbers in the phone number because the first 3 numbers are the area code. That's not going to be consistent across all of them, especially if we're talking about something like Eastern students. Most Eastern students are going to have the 509 area code. So we're going to get a ton of collisions from trying to map all of those to the same index. Whereas if instead we use the last 3 digits, that is more going to be evenly distributed. The goal is to get some kind of uniform distribution. Are people clear on what I mean by say something like a uniform distribution? I have a good visual example of it later on. So it would look something like this, where here we have values that are just about even, and the larger and larger sample that you would get all of these bars being approximately the same height. A perfectly uniform distribution has all bars at the same height. There's no variation, and this is what we would expect. We would want the same number of keys to be stored at every index. If we do that, then we have the most efficient structure that we can possibly construct. If there's variation and more of them are going to hash toward the middle of the table, or more of them are going to hash toward the beginning of the table, then we have an uneven distribution and we're going to see more collisions than we need to see. If you have a uniform distribution, you will minimize the number of collisions. So to give you an example, if we take what I'm going to show you with regards to how Java hashes strings, if you took the words in Tale of Two Cities and you were to apply the hash to them, the string hash that Java uses, you would get a pretty uniform distribution, which is what you would be looking for. All right, then we talked about how do we actually compute the hash function. So we want to create a uniform distribution wherever we can. So thinking about what do your inputs look like? What does your hash function look like? Over a large quantity of those inputs, are we actually hashing to a uniform distribution? That is an important question to ask if we want our hash table to function optimally. let's start going back over this at this level. So for primitives, we talked about for integers, we don't really need a different hash code. Because a hash code is just an integer, so for integers, we're just gonna return the value of the integer. There's not really anything better we could do for that. Granted, a lot of integers are closer to 0 than are at the extremes, so we could do something that would try to expandify them to that realm and then mod it by the integer, the maximum integer size, but it's just fine if you return the value of the integer because with respect to the table size, you'll probably get something that's fairly fine. For booleans, you want to return a prime if it's true and some other prime if it's false. And we can talk about the mathematical logic for why primes. We'll use it in a slightly different context.
Prime number?
Yeah, prime number. Ideally, your table size is also prime. We talked about for doubles, converting it into the associated 64-bit representation, and then we XORed the most significant 32 bits with the least significant 32 bits. And that gave us an integer, since we know that doubles are 64 bits, and integers are 32 bits. If you XOR 32 bits with 32 bits, you get 32 bits back. So you get a legal integer representation that is basically random. Because a double is not split perfectly 50-50 into the number and the exponent. We talked about there being two components to a double. There's the base and there's the exponent. It turns out that there's a lot more storage for the base than there is for the exponent, because usually our exponents aren't crazy high. We only need to store exponents up to about 300, whereas we need to store lots and lots and lots and lots of digits. So because of this, we have more of the bits being the base. So when you XOR 32 bits by 32 bits, you're actually cutting off part of the base and XORing it with part of the exponent, which creates something that's not particularly easily guessable based on the value of the double. So if you were to look at how to do it in code, this is the easiest, shortest one-line solution. So we have the XOR. I think that's where we stop. We're gonna talk about strings. Maybe we started talking about strings. Did we talk about it? No, I don't think we did. Like we stopped with doubles. So strings require just a little bit more work. We're going to compute the following function. So the hash is the first character of the string plus 31 to the power of the length minus 1 times 31 to the power of the length minus 1 plus up to the third to last character times 31 squared plus the second to last character times 31 to the first plus the last character times 31 to the 0, which is just 1. So it's basically just multiplying, basically you're taking each character and you're multiplying whatever you have by 31 and adding that, then multiplying that result by 31 and adding that, and then multiplying by 31 and adding that. So you're creating a unique integer based off of the string representation. And the reason we use 31 is not only is it prime, but it's a Mersenne prime. Mersenne prime means that it's 1 less than a power of 2, since 32 is a power of 2. It ends up being the single most efficient kind of prime that you can use, because anything that's a power of 2 is a bit shift and a subtract away, both of which are very easy for a computer to calculate. Bit shifts are constant and subtracts are constant. So it's very easy in two CPU cycles, you can get the value of a Mersenne prime. So that makes this computation as fast as possible. You get a uniform distribution as fast as possible. So you could use something else. It will work if you use any integer here, but it will be more uniform if you use a prime, and it will be more efficient if you use a Mersenne prime. So the code implementation of this, you just have the hash code function. We set the hash to 0, and then we just iteratively calculate this. So for each character, you're going to take the ith character and you're going to take 31 times the current hash value and add the value of that character. And that ith value of that character is the ASCII value of that character. We know that we can represent characters as integers based on their ASCII value. Have we seen that before? So 65 is capital A, 97 is lowercase a, and then they follow sequentially from there. So capital B is capital A plus 1, capital C is capital A plus 2, etc. So they follow right next to each other. And this allows you to hash strings that contain things like passwords, that can contain characters that aren't letters or numbers. Each of those have their associated ASCII code, which means that for any character that is in ASCII, we can calculate the hash code of an associated string, not just English words. And it should still adhere to a uniform distribution. So S of I is the ASCII value of that character, and we're going to calculate this function that's at the top of the screen iteratively. So there's a mathematical equivalence between H and this iterative calculation of H. Questions on string hashes? I'm not doing too much of the underlying mathematical motivation of why it works, because it's not particularly important from most programmers' perspective. Just know what to do. This will generate that uniform distribution. If you're curious, we can go over it in office hours. User types means the kind of object that you would create yourself. So if you were to create a person object, or an animal object, or any other kind of custom designed object, we're going to use the same kind of 31x plus y rule. 31 is popular again because it's a Mersenne prime. So what are you going to do? Just like we broke a string down into its individual characters, we're going to break an object down into its individual fields. So you're going to initialize your hash code to a small prime. Start it out at any value of a small prime. 17 works, any other small prime works as well. For every field in your object, you're going to multiply the existing hash by 31 and add that field's hash code. So if the field is a string, you will calculate the hash code of that field and then add that on. If it's an integer, you'll just return it and add it. If it's a double, you'll calculate the XOR of the first 32 bits with the second 32 bits. As you continue this process iteratively, you will eventually reach a final hash code after you've considered every field of the object, and you'll return that hash code. We talked before about the important parts of a hash code. So if two objects dot equal each other, they should return the same hash code. What does the dot equal for a user type do? How do you overload a dot equals to determine if two objects are the same? Let's say I have two different person objects. How do we just determine yes or no? These are the same, this is a deep copy of the same person object. Field by field, and check and make sure it's the same. So you verify that their .get class is the same class, and then you go field by field and compare their values. So we're going to do exactly the same thing when we're going to determine the hash code, because we want two objects that are deep copies of each other to return the same hash code. So it makes sense to go field by field. If you have a reference type, then you can just recursively call its hash code. If you have an array, you're going to need to apply the hash code of each element of that array, which is kind of what we did for strings. Since strings are just arrays of characters, and we iteratively went and applied a hash code to each character in that array. If we have an array of user types, we will calculate the hash code of the first object, And then multiply it by 31 and add it to the hash code of the second object and just continue to do the same thing. What happens if we overflow the integer by doing this? You can't multiply something by 31 too many times before you overflow an integer. Yeah, it just wraps around. You basically get a free modulus with an integer because it doesn't matter what the bits outside of the scope of the 32 bits of the integer are. You end up with just whatever the last 32 bits are, that's your integer. That's perfectly fine. We will see that we need to make a little bit of a special note for how to handle negative integers. Because let's say I want to hash something and the hash code turns out to be -10. Is that a valid index? What should we do about that? I'll let you think about that for a second. We're gonna come back to it momentarily. So here's what you do. If you have a basic array, you can use arrays.deep hash code and that will call it recursively on each element for you. So there is an existing built-in deep hash code. Here is how you would do the hash code yourself though for a user-defined type. This is a transaction object. So there is a string who, a date, when, and a double amount. So we start out our hash at 17. We reassign the hash to be the old hash times 31 plus the hash code for who. Then we redefine, we say 31 times the old hash plus the when's hash code. And then we do it again, we multiply it by 31 and add the amount dot hash code, but we need to make sure that the amount is cast as a double object. Otherwise, since the primitive double doesn't have a built-in hash code, we need to, if we cast it as a double, then we can just call that dot hash code, and that implements the logic from the double that we said before. Otherwise, we have to specify it ourselves again. So when you have, if you want to just call dot hash code on a primitive type, make sure you wrap it first, or you cast it as the wrapped type. Does that make sense? Because the double class has a dot hash code, but the primitive double does not. So you don't need to memorize, as an everyday programmer, you don't need to memorize exactly how all of these hash codes work. In general, the best thing to know is that everything that is built in Java has a hash code already. So call the existing hash code. You only really need to worry about implementing it for your own custom defined types. Questions so far? How much sense are we making so far? I just kind of want to get a sense of to where the class is, just on hash codes in general. We will get some examples of this towards the end of this slide deck.
Is this in the book at all?
I actually don't know. I did not pull any of this from the book.
How similar is this types of hash codes to like cracking a password hash codes?
So, yeah, passwords are, it's not quite the same. You can do something like hash a passcode to store it, or a password to store it somewhere, but usually they are, there's some separate algorithm for doing that. If we all had the same hashing, it'd be easy to undo. So my recommendation would be to take a security class. Basically, you have keys at each end, and you can you can encrypt keys and use that kind of as a handshake for that process. But it's a more complicated topic than just hashing. It's a great question though. All right, so reducing all of this down to the bare bones, what you need to take away, a hash code, despite there being lots of different ways to calculate one, is just an integer between the integer minimum value and the integer maximum value. So the integer's minimum value is negative 2 to the 31st, and integer's maximum value is 2 to the 31st minus 1. Do we know why that is? Why isn't it just negative 2 to the 31st and 2 to the 31st? Why is it 2 to the 31st minus 1? Good guess.
This side of it.
It's because 0 is a positive integer, according to integers. So everything that starts with a 0, the very first bit is a 0, is a positive number. Everything that starts with a 1 is a negative number, and 0 starts with a 0, because it's all zeros. So it takes up one of the spaces of a positive integer. A hash function is just a way to go from this hash code that is any possible integer into an index into a table that gives you some other integer between 0 and a table size minus 1, which is every valid index into that table. So if we had a table size of 10, then we would want an index between 0 and 9. 0 and 10 minus 1. So we're going to squishify all integers into something that is the table size basically, between 0 and the table size minus 1. We've already discussed, but maybe we can recap. What is the best algorithm for converting a hash code to a hash function? You know, think of as a formula or an expression. It's not a complicated algorithm. It's just an expression. We said modify the table size. If you modify the table size, you get something between 0 and the table size minus 1. Say we have a really large integer, and we had a table of size 10. Let's just choose 9999999. Where would that fit in a table of size 10? What index would we hash it into? Index 9. Mod something by 10, it's just the last digit of it. So it doesn't matter what anything is except for the last digit. Whatever the last digit is, that's going to be the place that it gets stored in the table. Anyone see an issue with this? There is an issue with this. Something that I hinted about a few minutes ago. Yeah, we have a negative number. What happens if we mod a negative number by the table size? If we mod it by the table size, then we still do get something between 0 and 10. So on the other hand, well, yeah, we can get something negative, which would be a bit of a mod it by the table size and get something negative. So if we instead use the absolute value of the hash code, mod the table size, now we get something strictly between 0 and 10. There's still an issue with this, but now the issue is significantly smaller. If you were to implement this, maybe once in your life, in your entire life, in your entire experience with this, you would come up with a single bug that you would have a really hard time isolating why it is. Can anyone think of what that 1 in a billion issue is? Actually, about a 1 in 4 billion issue. What happens if we take the absolute value of exactly -2 to the 31st? Yeah, we would be taking the absolute value of -2 to the 31st, which is 2 to the 31st, which is out of bounds. So we can't hash anything with exactly that value. So I searched around on the internet to see if I could find a string that hashes to exactly -2 to the 31st, and it turns out that Polygena lubricants hashes to exactly -2 to the 31st. That was really hard to find. And every few billion hashes on average, that's a really fun bug to find. So if you want to do something about this, you just really wanna decide if this hashes to exactly -2 to the 31st, do something about it. So the very best answer to this is you're just going to take the bitwise and of the hash code and the largest possible integer. So this is just an hex, yeah.
Could you just do if string equals polygenic lubricants?
There are going to be more of them, but it's only 1 in 4 billion strings. But that's only for strings. You could have a user defined type that happens to hash to that, because we don't really have a ton of control over that. So I wanted to find some kind of string that did it, but 1 in 4 billion hashes.
Actually, like kind of a word too.
Yeah. I actually did not try to look it up to see what this might be. If it's a thing, but at least sounds like a thing.
Yeah,
I'd never heard of it before.
I don't know if I wanna look that up.
I don't know if I want to, if I searched it through either, honestly. But one does exist.
Under what circumstances would you use the hashes?
Yeah, right. So the best answer is just to bitwise and it, and all this is doing is saying, if you have a key that is exactly -2 to the 31st, just hash it as 2 to the 31st minus 1. That's okay. One of these 4 billion things will have 2 different ways to generate the same hash code. Not the end of the world. So this is the and there is just the bitwise and operation. So if you're taking discrete, you're just taking you're taking the bitwise representation, and the answer is 1 if both of them are 1, and the answer is 0 otherwise. And -2 to the 31st is just 1 0 0 0 0 0 0 0 0 0. So all you're doing is taking exactly the same number that's there and potentially flipping between, that's the last bit, that's the only thing that matters. So rather than error, the 1 in a billion case, it'll set the hash code, it's actually not to 0. I made a mistake there, but it'll set the hash code to something else. So the goal is to create some kind of uniform hash. We want to make sure that whatever we're using, we want an equally likely chance to hash it between 0 and our table size -1, regardless of what our table size is. So we can now visualize each array index as some kind of bin, and each value we want to store as a ball. We want to be doing this as random as possible, throwing balls into bins, such that after we're done, each bin has the same number of balls. So this would be something like we would expect if we had a table size of 16 and we threw some balls into it. You can't do better than random. You just can't. You can't bias it in such a way, because that bias is going to be individual problem based, it's going to be individual table size based. So the generic best thing that we can do is basically create a uniform random distribution. On the other hand, we may know a bit more about the underlying structure of our data. Like for instance, if we're trying to sell tickets to a sporting event that's happening tonight. And each of the tickets are sequential integers. We know a bit more about the underlying representation of our data. If we wanted to, for some reason, hash the ticket number. So if you know more about the underlying data, there's occasionally some more intelligent stuff you can do. But we want to do something that looks kind of like I showed you earlier. If you use Java's built-in string hash and hash tale of two cities, you get pretty equally distributed bins. And this looks great. This looks like a very successful hash with a way too small table size. So if we use an array, of course, we can only store one element at a particular index, which is a problem. And if we try to store multiple objects that hash to the same value at the same index, we get what we call a collision. Now it's time to brainstorm and see if we can come up with any ways that we can avoid collisions. I'll start with a stupid answer. Uses a quadratic amount, we just use a quadratic amount of memory. If we do that, if we use so much memory that we can't possibly store everything everywhere, and on average, we're gonna be looking one place for everything, great. But of course, it's infeasible in practice. So can anyone solve this problem intuitively? I have to ask everyone, because maybe you come up with something that nobody's ever thought of before, and it'd be really cool. Exactly. No, not me. I work with you, you publish it. Thoughts? What could we do? How could we avoid collisions? We're going to talk about two ways. One is an algorithmic technique, and one is a storage-based technique. Or a structure-based technique. We have the tools, we've seen the tools, yeah.
Well, couldn't you do something like every time an object gets allocated, there's like some sort of pool of, like it already is given like a hash, and then it checks like the pool to make sure that it doesn't already exist or something.
Okay, I like that. So we know stuff that's been hashed places. Sure, we go to hash it and there's something there.
Just like add one to the hash function and see if it collides again.
That's that's the algorithmic technique we're gonna talk about. You just look to the next position, and then look to the next position, and then look to the next position. We call this linear probing. What else could we do? That's the algorithmic technique, and there are some variations to that algorithmic technique to avoid things like clustering. We'll talk about that. But structurally, what could we do? Yeah,
You try to like make an array that is more like a byte, like it stores different elements to the same hash.
we know how to do that already. What structure do we know that stores a bunch of elements? It's a great idea. It's exactly what we want to do. A linked list. A linked list can store an arbitrary number of elements. So what happens if we had an array of linked lists? And each linked list represented a particular place that we could hash things to. When something hashed there, we just add it to the linked list. And that way, if we wanted to check if something is in it's been hashed before, we go to a place and we have to worry about how long is that linked list. Because obviously we don't want a linked list that's as many elements as we might be hashing, that's gonna take a linear amount of time to search. But if we spread those out evenly across the entire table size, then can we get a better guarantee than a linear number of queries to figure out whether something is hashed there? We'll talk about that in more detail. So when we have a collision, we need to handle it preferably efficiently. We're gonna talk about these in order. We're gonna talk about linear probing, then we're gonna talk about using this array list of linked lists. We're gonna start being able to combine the structures that we've talked about to create more complicated structures. So linear probing says when we have a collision, we're just gonna look at the next index mod m. So if we fall off the right end of the array list, we're going to go back to the beginning. That's all that mod m there means. If we had a table with size 10, the next element we look at from index 9 is index 0. It wraps around. And you just continue to do this until we find an empty index. What do we think? Benefits of this, detriments of this? Yeah,
You just stuck behind like a super long block of continuous.
yeah, we could absolutely, if we were gonna do worst case analysis on this, what does the worst case look like? Let's say I wanted to ask, does this table contain the integer 19? And we have a table of size 1001. Let's say 19 hashes to index 406. There's something already at 406 and it's not what I'm looking for. I have to look at index 407. There's something there, but it's not what I'm looking for. I look at index 408. There's something there, but it's not what I'm looking for. What's the worst case?
Never mind it.
You loop all the way back around. The table is completely full of elements that aren't what you're looking for. So in the worst case, we have a linear amount of work to do. It's based on the table size. We have to look at every single element in the table. When could we stop early? If there's nothing there, if you look somewhere and just like, there's nothing there. What happens? We'll look at this in a second. So we talked about this being a long array of, we're gonna say that this is index 406, 407, and 408. Let's say when I went to go insert 19, there was something already here. And so I had to insert it here. And there's something already here. There's 9. And then when I finally get to, see, I said 19. Now we store 19 in 408. What happens if I go delete 9? All of these hashed originally to 406. I go to delete 9 and I get rid of it. I go look for it here and then I look for it here and I find it and I delete it. What happens when I now ask about 19? We have an empty space, so we return false. This does not contain 19. So without further work, I don't think we can say, if it's empty, there's nothing we can do, or it's not on the table. I need, but I'm lazy. So the thing to note, and to really take note of here, is that how expensive this is going to be to be able to put a new item into the hash table gets more and more expensive. It approaches linear as the table fills up. If the table is empty, there's nothing in the table. How long is it going to take to insert? Constant. There's nothing there. There's no possible collision. If the table is completely full, it's gonna be linear. Because we need to find the one place, or we need to know that it's full, which is gonna require us to iterate over every object that's already in there and find 0 open places to put the new thing. We talked about removal, we talked about the big issue with removal, so you hash into the table, do a linear search for the key you're looking for. But there's a big issue with it. If we wanted to do a contains on the hash table, so we have a query and we want to say, is this query stored in the table? Then we would like to be able to say that seeing an empty array index says that the query is not in the table. But it doesn't because of delete. So the example that I just gave you, add 2 elements that hash to a particular index, remove the first and try to access the second. And we'll find that the second is hidden behind an empty index. So if you wanted to implement linear probing, and again, we'll see some of this and we'll get some examples of this probably tomorrow. We want to see some implementation of linear probing. And so we end up with something like this. So we're gonna set a table size. We have our M at 30,001. We have a list of values, we have a list of keys. And then we want to get an associated value from this hash table. So we're going to put in the key that we want to go find. And then we're going to hash the key and then continue to add 1 to the index, mod M, add 1 to the index, mod M, add 1 to the index, mod M, until we find it. If the key at position I equals the key that we are looking for, then we want to return where it was. Sorry, return it, saying, yes, it was in our table. Otherwise, we return null, it was not in the table. So that's what get or our contains, they're both the same thing, would look like. If we wanted to put something in the table, it would look more like this. We're going to hash it. We're gonna go see if something is there. If something is there, we're gonna keep looking. Add 1, mod M, add 1, mod M, add 1, mod M. And you can see that we have different keys and values. And we see that delete creates an issue. So before deleting S, we hash S and we get to index 4. This is more of a map. And we go search for it and we find it at index 6 and we delete it. But now if we try to hash H and get 4, now we find that there is something missing. And H is actually in the table, but we can't go find it because there's a hole there and we have to search now the entire table because we don't know for sure if we've been deleting it all, if anything's in the table or not without searching the whole table. Does that make sense? Why we need to search the whole table? So we want to talk about this in more detail because there is something much better that we can do. The first solution that you may come upon is to use the concept of a tombstone. A tombstone says that something used to be here, but it got deleted. And then from the scope of contains, we will say, this is something that we are not looking for. But from the scope of add, Now it is something that we can add to, since it's empty. So. If each one of our array indices is an object. Then this tombstone just becomes a Boolean field to that object. It's kind of a flag that says, if this is empty, did something used to be here? So insertion treats the tombstone as an empty element. If we want to go add something to the hash table and we eventually find an empty place for the tombstone, we can fill it, no problem. Deletion, on the other hand, normally we want to stop when we find an empty index. But if we find somewhere with a tombstone, we're gonna say, keep looking, because what you're looking for may actually be after the tombstone. For contains. For deletion, when we do delete something, we want to set that tombstone flag to true when we do go delete it. All right, we are out of time. We're gonna come back and finish this off tomorrow. I think we're gonna be able to do that and move on to the next topic. I know this is far and away not the most exciting topic, but I think when you see it work, it's a really cool, efficient structure. That actually is the heart of things like a potential implementation of a set or the potential implementation of a set. So let's see the uses of these. We'll start at the bottom.